Okay, so today we're going to be talking about Calderon-Zygmund distributions and these operators that you make from Calderon-Zygmund distributions by convolution. So you take some function and you convolve it with a Calderon-Zygmund distribution. And this kind of operator is called a singular, in general it's called a singular integral, because the kernel that you're convolving against is it blows up. It's a non-integrable kernel, basically. So this is actually a huge idea in analysis, and its generalization. So this is a generalization of the Hilbert transform, but there's sort of like many different generalizations of this concept, and even now, this is not. I think the way we're going to talk about it today is a little bit old, but even today, this is a sort of a hot topic. So in the world of harmonic analysis, people are still concerned with the behavior of singular integrals, and still going after new results. Just a couple of years ago, there was sort of like a big climax in the theory when something called the A2 theorem was proved by this guy, Dilation. Anyway, so it's still a very active. This is an active field. And so what I want to say is before this is that what we're going to see today is just one particular kind of singular integral, and then there are many other kinds. So don't get stuck thinking like this is a singular integral. That's a mistake. There's a lot of things that are called singular integrals, different kinds of things. A lot of generalizations. Okay, so Calderon. So let's start off with the following definition. You have some function, some smooth function, and it's supported in the unit ball. And say that for some n, so n is 0, 1, 2, something like that. Suppose you know that, so if for some n, the supremum of all the derivatives, so for all, over all x, so you're taking the L infinity norm of the derivatives, okay, and you're doing this for all alpha of size less than n. Okay. If that thing is less than 1, for all alpha of less than n, then we call phi a C super n, Cn normalized function. So this is mainly a condition on the normalization, right? If you have any bump function, on the unit ball, right? Any smooth function on the unit ball, then these things are going to be bounded. Right? So if you divide by some constant, right? If you divide by the largest constant that you get in these bounds, then you're going to get a normalized bump function. So any bump function is going to be some multiple of a normalized bump function. So this is mainly all this is saying that we want these things to be all less than or equal. Okay, so nothing So I'm going to erase this, if that's okay. Is that all right? Long function. Now we come to the main definition. So let A be a regular distribution. A be a regular distribution that is agrees with some smooth function away from the origin. Okay. And then suppose that K satisfies two conditions. The first is this differential inequalities condition that differential inequalities that the derivatives for all A behave like this for all alpha. So this is talking about control on the size, right? Control on the decay of all the derivatives, and two, satisfy cancellation condition. That is that for some n greater than equal 1, they exist in alpha and they exist in A, such that the supremum of K applied to phi R is less than or equal to A for all Cn normalized belt functions. For all normalized belt functions, where this piece of R is the standard dilation as before. It's the supremum over all dilations, supremum over all dilations of the belt functions. You take K and you apply it to these guys, and you always get there's a uniform bound over all of them. So if you satisfy these two conditions, then we call K a Calderon-Zygmund distribution. Calderon-Zygmund distribution. Okay. And so we're going to need here. So the useful proposition will be this one. A bunch of conditions that are equivalent to being a Calderon-Zygmund distribution. So you are K is a Calderon-Zygmund distribution. If and only if K is a temporary distribution. Such that its Fourier transform, which we denote by M, is C infinity away from the origin. And satisfies there's a small typo in the book. It has this to the negative alpha. I think it should be this to the negative size of alpha. I don't know what that would mean. I don't think that means anything if you have a real number to a multi-index. Yeah, doesn't make sense. Does it? That's right, right? Yeah. Okay. 3. K is a regular distribution. Such that K hat is a bounded function, and K, little k, the function that, the C infinity function that big K agrees with away from the origin, satisfies the differential inequalities. So this is basically giving you sort of like conditions on K to be a Calderon-Zygmund distribution in terms of the distribution itself, and what that means in terms of its Fourier transform. And these turn out to be equivalent. That is, you know, if your temporary distribution and your Fourier transform satisfies these conditions, then that means that your guy is a regular distribution, and it satisfies cancellation and the differential inequalities, and et cetera, et cetera. And equivalently, that's equivalent to saying that your Fourier transform is a bounded function, and K satisfies these differential inequalities. It's just different characterizations of the Calderon-Zygmund distribution. And we'll sort of use all of them. If you know that you guys have Calderon-Zygmund distribution, then you can use all of these properties, which is good. Okay. Okay. So. Okay, before we prove this, we'll make an observation that the class of Calderon-Zygmund distributions is invariant in the dilation. In the following sense, that if K is a Calderon-Zygmund distribution, then the dual dilation of that distribution, right? And remember, the dual dilation is given by taking K on the dilation of the test function. Then the dual dilation, so A, this on positive A, is also a Calderon-Zygmund distribution, and with the same bounds. With the same bounds. Okay. So that is, if you dilate your guy, then in fact the function corresponding to that guy is going to satisfy the same thing with the same bounds. Okay. This second one is actually showing that the dilation, showing that so you know, as it for an easy part of that, you say, well, you know, if you take a dilation here, and then you throw this dilation, you have a Calderon-Zygmund distribution, and then you take some dilation of it, right? In this case, it's trivial, right? Because this is just going to be the dilation of this, right? So you're going to get the original die. You're going to get the original die applied to some other dilation, but you're taking the supremum over all dilations, and so the bound is going to be the same, right? So that's trivial, showing that the dual dilation of the distribution satisfies the same cancellation bounds is trivial. That's trivial. The first part is also not difficult. You say, well, let's look at consider part one, right? Let K, if K denotes the function associated with big K, then the function a to the minus d k x over a, which let's call that g of x, is the function associated with k a. And then, when you differentiate that, right? When you differentiate that, well, what you get, you're going to get that it's controlled by a to the minus d c alpha, where this c is from k. Right? This is the c alpha from k. You're going to get x over a to the negative d minus the size of alpha, and you're going to get 1 over a to the size of alpha, right? And so that all that stuff cancel out, and you get exactly the same bounds just by the chain rule. So just by the chain rule, you're going to see you see that that you get the same bounds. Because you get the derivative of k, you get the alpha derivative of k evaluated at x over alpha, right? But that thing is controlled by c alpha times x over a to the minus d minus the size of alpha, and then you get that constant, and you get 1 over a to the negative size of alpha, right, from the chain rule. So that gives you, this gives you you can also see this from on the Fourier transform side, right? If you're thinking of Calderon-Zygmund distributions on the Fourier transform side, so on the Fourier transform side, if you take the Fourier transform of the dual dilated die, you get the dilation of the Fourier transform, where m is the Fourier transform of K. So you can see that's an easy calculation. And then in the same way, you get that if you take the derivative of that die, well then, it's controlled by c alpha prime, make c negative. A to the size of alpha. anyway, the same thing happens. It's just a chain rule. Okay. So the point is that whenever you have somebody in the Calderon-Zygmund class, it and all its dilations satisfy exactly the same bounds. Exactly the same bounds. The constants don't change. And that'll be very helpful. Okay. So let's do the proof for the first one. That one applies to. So you want to show that if you are, Calderon-Zygmund distribution, then K is a tempered distribution, and its Fourier transform is to infinity and satisfies some differential inequalities. Okay. So the fact that K is a Calderon-Zygmund distribution means that it satisfies. Right, remember that we satisfy these differential inequalities. So since K is Calderon-Zygmund distribution, we know that that K itself satisfies this sort of decaying, and that implies that it's tempered. So that it's a tempered distribution is easy. So K is that's easy. That K hat is a C infinity function, follows sort of the standard argument. Right, you take, and we've seen this argument several times already. You split K into K naught plus K1 using some cutoff function where eta is supported in the unit ball and is constantly equal to 1 on the ball with radius a half, right? And then we've seen this thing before, right? This guy is compactly supported. You take its Fourier transform. It's a C infinity function. This guy is right. This guy is over here. You use the fact that you use this Fourier transform argument to get bounds on it, and blah 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 blah. We've done this. You just do the same argument. So showing that the C infinity function follows standard arguments. So the main thing in this is to show, main part is to show that that the differential inequality is hold. And for that, we'll use the dilation and variance of the class of Calderon-Zygmund distributions. So claim suffices to show that the inequality holds for C of size 1. So, right, because once you have that, using the dilation invariance of the class, you can get the result for everybody. And because this is a pretty common sort of argument, and we haven't seen it before in this class, let me lay it out for you. So we have this reduction using the dilation invariance. Okay, so suppose we have it. Once we have the inequality for C equals 1, you say, okay, well, suppose you have some zeta of size A. Then let C of course be 1 over A times zeta. Then of course C is size 1. Right? And you apply then so we're trying to we want to show this thing for K, right? So let M be K hat. Let M be K hat, and we want to show the inequalities for M. Okay. So now we use the dilation invariance, and we say, okay, let's look at the dilated distribution. Right? We know that is going to satisfy this condition where the C alpha is the same as for K hat. But then, of course, the alpha that's to say that we get the alpha of M evaluated at AXC times A to the size of alpha. Using the so this is the sorry. So when we get that this is less than this, so we just take the derivative of this guy, and that means that that's to say that A alpha M evaluated at zeta is less than or equal to C alpha absolute value of zeta to the negative alpha. Okay. So that means that gives you the inequality for guys that are not of size 1. So it's simple. So the dilation invariance of the class allows you to just reduce down to proving the inequality for proving the inequality on the unit ball. So right, so here. So suffice it to show that for C equals 1, we get this is bounded by some constant. So again, we do the same sort. So use the script k equals k naught plus k1. Again, since k naught is compactly supported, we know that k naught at c equals k naught of some bump function where p of x equals beta x e to the negative 2 pi I x times c. So this is a result that we solved earlier. That the Fourier transform can be realized as taking the distribution and applying it to this bump function. Now, phi is a multiple independent of c of some c and bump function. So, by the cancellation condition, by cancellation condition, we know that this thing is bounded in size by some constant. So that gives us that. That this part of the Fourier transform of the distribution is bounded by some constant. So we get that this part of the distribution is bounded by some constant. Okay. And one can similarly, I didn't check this to be honest, but I think it's not hard to see. I believe it's not hard to see. That similarly one can show that all the derivatives are also bounded by some constant. So that gives us that this part of it is controlled by a constant. Right? So the other part we need to show that this part is controlled by some constant. So I guess right. So note that K1, which is equal to 1 minus eta times little k, is supported outside ball of radius a half, because eta was equal to 1. Eta was equal to 1 on the ball of radius a half. Right? And then we use again the sort of usual estimate that or the usual quality absolute value of c to the 2n, applying the Laplacian to this, taking the Fourier transform. Right? You take the Fourier transform of the Laplacian applied to some polynomial times the guy, and we get that it's equal to c to the 2n times the derivative the Fourier transform of K1, right? So this we've used over and over, right? If we're trying to get some bound, we're trying to get some control on the Fourier, on the derivative of this guy. Well, we can control this. We have this useful inequality. Flip it over. Okay. Now translating that into the Fourier transform, right? That gives us that this is bounded by the integral over k greater than x in size greater than half of the function using the differential inequalities, we get that this thing is controlled by some constant times x to the size of alpha minus d minus 2 dx, which is finite for large enough. So what that gives us is that for C of size 1, then this thing is controlled by some constant. And that's what we want. I'm cheating you a little bit. I think I'm cheating you a little bit because eta is 1. So here's eta, right? And k1 is 1 minus eta times k. Right? So outside of the unit ball, k1 actually is k. Right? Outside of the unit ball, k1 is k. But between 1/2 and 1, it's not equal to k. But that's only going to contribute some small constant anyway. So maybe plus c. It's still finite. Okay, so that's it, right? You get that. We show that for c equal 1, then the Fourier transform satisfies the decay, the differential inequality, and that gives it to us for all dilation and variance of the class. So I think at least for right now, I'm going to skip the other two parts of the equivalence to show that. So we've shown that 1 implies 2. We need to show 2 implies 3, and 3 implies 1. 3 implies 1 is easy. 2 implies 3 is not so easy. But for now, let me skip it. I may come back to it later. I'd like to go on to singular integrals. I suggest you read the comments on the bottom of 188, which are useful. So maybe the most interesting one for you is that if Q is a parametrics of an elliptic operator of order n, then for all alpha of size less than m, d alpha q is a Calderon-Zygmund distribution. You, in partial differential equations, you create these parametrices and you want to convolve with the parametrices. Well, convolution with the parametrices and their derivatives will be a singular integral. That is to say that these singular integrals arise naturally in the theory of partial differential equations. So, if you are interested in this sort of thing, that's sort of is a good idea, or it behooves you, if I may use an old-fashioned word, it behooves you to study both variance, PDs, and harmonic analysis. Yeah, every 4 years, for example, there's this international conference in Spain where everybody in the world of harmonic analysis gets together. But it's really called the Harmonic Analysis PDE Conference. Anyways, it's a good idea to know both areas. I wish I knew more on PDE side, on both sides. Okay, so singular integrals. So, like I said before, we're going to consider convolution. We'll consider convolution operators of the form TF equals K convolved F, where K a Calderon-Zygmund distribution. And on the Fourier transform side, you'll have something like this: TF at equals n plus f at. Okay, so that is on the foot. So these operators are what are called multiplier operators. You take some function, you flip it over to the Fourier transform side, you hit it with some function over there, and then you bring it back, right? So it's called a multiplier operator. Now, what this means exactly is not exactly clear, okay, at this point. But it'll be. We'll have to create what this means ourselves. Okay, so maybe that remark is sort of cryptic, but you'll see what I mean in just a minute. Okay, so write the same thing again, let T be defined on F in the short class by, let K be a Calderon-Zygmund distribution and let T be defined by as convolution of the of that tempered distribution against the Schwartz class function. Then T extends to a bounded operator on LP for P between 1 and infinity. So we'll show that it's bounded on LP for this dense subset, and then as usual you can extend it to LP for the full space. So I think we'll do the whole proof, but let's do a part of the proof. So proof, this part, the LP theory. You say, well, F is in the Schwartz class and K is tempered. Right? So we know we had this theorem from before. It was proposition 1.5 that K convolved with F is a C infinity function, slowly increasing C infinity function, and that TF that K convolved with F hat equals F hat K hat. F hat K hat as distributions. As separate distributions. So this was the proposition we had before. Okay. And so now we want to show that T is bounded on L2, or I'm sorry, on S in L2, in the L2 sense. So you say, okay. Okay. So in the book, there's this line: TF L2 equals TF hat L2 equals bounded by the supremum of K, the supremum of K, supremum of K hat, supremum of K hat times the L2 norm of F hat, which is bounded by A times the L2 norm of F. Okay, so this is a very terse line. And it was a little, anyway, so what does this mean? This part is clear, I think, right? Remember, if K is a Calderon-Zygmund distribution, then K hat is a bounded function, right? That was part 3 of those equivalences, right? K is a bounded function, and so this A is going to be the L infinity norm. A is going to be L infinity norm of K hat. Right. Okay. So what's this part? The Fourier transform, the L2 norm of the Fourier transform of TF, right? Right, TF hat, so this thing here is TF, right? This is TF hat, right? TF hat is F hat K hat in the sense of distributions, right? So if we're looking at the L2 norm of TF hat, what that means is that you want to consider TF hat and then acting on L2 functions of norm less than or equal to 1. Right? The L2 norm of this is going to be the supremum over these guys at L2 norm less than or equal to 1. Right. Okay. Now this thing acts as f hat k hat. We can replace this by f hat k hat because as distributions, that's how these guys act the same, right? Okay. So now that gives us this, right? Because this thing here is going to be controlled by the supremum of the absolute value. I'm sorry, this should be absolute values. This thing here is going to be controlled by the L infinity norm of k times the supremum of this thing, but that's going to give you the L2 norm of f hat. Right? So this equality requires a little bit of interpretation. Right? TF is a in any case, that shows you that TF hat actually is an L2 function, which means that TF is an L2 function. Have I made a mistake, Chen? Am I missing something?
I think maybe you don't have absolute value starting each one. Yeah, I think it also works.
It's like this.
Yeah, I think so.
Okay, sorry, thank you. Yeah. Then I'm not sure if it works. Does it work? Does it still work? Right, because then how do you
Yeah, I mean, this is a definition of the norm, right? And you can put an absolute value sign inside each line, so it's this.
But then you don't get the L2 norm of f out. Like you can certainly by the triangle inequality you can put it in and then pull this thing out.
Yeah, if you can put chaos outside,
yeah,
you get it out.
Yeah. Okay.
Yes.
You get that? Right. But then how do you get this? Do you want to get the why is this? Why is that right? Why do you get the
F is because phi is in phi is in L2. May I write something? I just think that the norm of Fourier transform f hat equals super like f hat times psi.
So this is just equal to the
Yeah, I think
is that right?
here, but
F is a Schwartz function.
yeah, actually this works. Yeah, because F is Schwartz, so it's in L.
It's in L2.
Yeah, it's in L2, but F. Yeah, I mean,
right.
Isn't that just the
Yeah,
definition of normal?
Yeah. Yeah, okay, that's right. Yeah, yeah, of course. Okay, so that, okay, thank you. Sorry. Okay, okay. Yeah. So, okay, so it requires a little bit of thought, I guess, but in any case, what you see is that this guy is an L2. And that tells you that by the Planchel theorem that these things are equal. So this guy is also an L2. Okay. So what I mean to say is that it's not evident from the beginning, I think, that no, maybe just okay. So in any case, you get that T is bounded on L2 when restricted to Schwartz class functions, and so you can extend get T bounded on L2 for all functions in L2. So you get the L2 theory, and then the line of the proof basically follows an argument we've seen before, where we'll show that that T satisfies weak type inequality. Like the weak type inequality satisfied by the maximal operator, maximal function. And then we'll interpolate between the weak inequality and the L2 inequality. Okay. That will give us P between 1 and 2. And then we'll use a duality argument to get the result for P between 2 and infinity. So to get the weak type inequality, we'll use the Calderon-Zygmund decomposition. So it'll be a little bit different from the decomposition we used before. I think this is actually the original one. t behaves on L1 functions. Given any alpha greater than 0, there exists an open set E sub alpha and the decomposition F equals G plus B, the good part plus the bad part, such that the size of E alpha is controlled by C over alpha times the L1 norm of F. 2, the size of G is controlled by C times alpha for all x, at least 80. And 3, E alpha can be expressed as the union of cubes, where QK are cubes with disjoint interiors. Further, the B from before will equal the sum of these things that are like atoms, with each BK supported in QK, and such that one, each of them satisfies cancellation condition, and two, the L1 norm of BK is controlled by C alpha times the size of Q. That's to say that the average of the thing is controlled by C alpha. Proof is sort of along the lines that you've seen before. You let E sub alpha be the collection of x where the Hardy-Little maximal operator is bigger than alpha. Let me make a comment here that this is actually the uncentered Hardy-Little maximal operator. So previously, when I defined the Hardy-Little maximal operator, I said you take these cubes, or you take these balls. You can take other cubes and balls. You take these cubes that are centered at x. Actually, we will use the uncentered one, and actually we have been using the uncentered one all along. So I'm sorry to have misled you. Okay. So let E sub alpha be the place where the Hardy-Little maximal operator is large, and we know F star satisfies a weak type estimate. Right, so that tells you that the size of this thing is controlled by whatever else, C over alpha times the L1 long term. Right, so that's part one. Cool. Yeah. Part one is proved. Okay. So we have this E alpha. It's an open set. And you do the Whitney decomposition on it. So use the Whitney decomposition on E alpha. And recall what that gives you. That gives you decomposition of E alpha into these cubes with disjointed interiors, right? So you get the cubes with disjointed interiors, but better than that, such that the distance of each cube to the boundary is comparable to the diameter of the cube. distance of the cube to the boundary is basically, it's trapped between, some multiple of the diameter on the bottom and some multiple of the diameter on the top. So the distance to the boundary is comparable to the size of the cube. Okay. The closer you are to the boundary, the smaller the cubes you're going to have. Okay. Now let's define G. Let M sub k denote the average of F on Q sub k. Right? And we define G as we did before. G is going to be Mk if X is in Qk. Right? So whenever you're in one of these cubes, you're going to define G to be the average there. And it's going to be Fk if X is in no cube. Right? So if you're not in that set where the maximal function is large, right? If you're not in the set where the maximal function is large, right? So if you're in the set where the maximal function is small. Okay. So notice. So let's go for part 2 here. Sort of along the same lines as before. Right. If X is in the place where the maximal function is small, if X is in the place where the maximal function is small, that means that the average over every cube is less than alpha. Right? The average of the function of F over every cube is small, right? And that forces the function there to be smaller than alpha in E. So there's a theorem involved here. It's called like the differentiation theorem. I think it's called the Lebesgue differentiation theorem. But we've actually encountered it. We've used it in this way before. The averages over all cubes is small. That forces the function at that point to be small. Okay. So if X is there, if you're in the place where the maximal function is small, then f of X is small, right? That's G. Right? G is f of X on that set. So on the set, on this place, the bound is we have the bound. So getting the bounds on G. So if X is in E alpha, right? If X is in E alpha, then X lies in some cube, right? Right. So let's say X lies in Q sub k, then G of X is the average of F over that cube. That was your MK. Right. But you know that there's some point let xk bar be a point in E complement, E alpha complement, closest to qk. Okay. So there'll be some point here that's closest to qk. Say, call this by xk bar. Right? We know that the distance from here to here is comparable. This distance is comparable. This distance is basically the diameter of qk. Okay. Let's just say, for simplicity, that it actually equals the diameter of qk. Okay. Right. Then look at the absolute value of MK, right? That's controlled by, of course, this, right? But that's controlled by, let's take, basically you take a ball of, you take the ball that's containing this point and containing all of qk. Okay, let's call it qk total. Qk total. Right. So that's controlled by 1 over qk, the integral over qk total. Right. I'm going to multiply on top and bottom by the size of qk total. Right. And I know that this number is smaller than alpha, right? Because this is controlled by f star x bar is smaller than alpha. Right? Okay. But this ratio here is controlled by some constant. Right? In my picture, it's 4. Because the distance of xk to qk is smaller than is comparable to the diameter of qk. You know, the ratio of these volumes is controlled by some constant, right? By some universal constant.
That's what comparable means?
Well, so
What do you mean by
the distance of xk, qk to this thing will be bounded above and below by the diameter by some multiple C1 and C2. That's what I mean by comparable is that you know it's bounded below by some multiple and bounded above by some multiple. Okay. So that gives you that this thing is bounded by some constant, and so you get this whole thing is bounded by that the absolute value of mk is controlled by C alpha. And so we see that G, right, G of x is controlled by C times alpha, right? So that gives us the second. Okay, I guess I'll stop here and we'll finish this up. We'll finish up with Calderon-Zygmund for our session next time.